finish off 2.2 on factorial notation and permutations, and specifically today what we're doing is the permutations part of that. So there's two big types of counting problems. One's called permutations and one's called combinations. And the difference of them has to do with whether order matters. So with a permutation is an arrangement of objects in a definite order. So the order you put them in really matters. Another way, I guess a memory way to help this is order matters or position matters. Why is that a memory device? Because permutation starts with a P and position starts with a P. So if the order of something matters, then it's a permutation. If order doesn't matter, then it's a combination. So what would be an example of something when order matters? Well, how about when you use your lock at school and you go from one number to, let's say your combination at school is 13, 28, 50. Imagine if that was your combination. Aren't you freaked out right now? Okay, anyway. If that's your combination, 13, 28, 50, can you put those numbers in any order? Like, could I go up to your lock and put 28, 50, 13, and would it open? No, this is the only way it would open if you put it in this order. So order matters there. So this is kind of ironic because we call those locks a combination locks, but really they're permutation locks because order matters. Okay, so there's three different types of permutation questions basically, and we're going to look at two of them today. The first type is when you have a number of permutations of n distinct objects taking all of the time. Now that sounds complicated, but actually you've already done this. This is a question where you have a bunch of things and you want to rearrange all of them. You want to see how many ways you can arrange all of them. So for example, this question here, there are 10 different books. How many ways can they be arranged on a shelf? So you're going to take those 10 books and you're going to put them on a shelf. So we're going to put all 10 books. We've got 10 spots to put them in, right? There's 5, 6, 7, 8, 9, 10. And you know how to do this. In the first spot, if we have 10 different books, how many books could we choose from? How many possible books can we put in that spot? 10. In the second spot, how many books could we put there? Well, we've already put one in the first spot, so there's only 9 left to go in the second spot. In the third spot, we've already used 2 books, there's only 8. There's only 7, there's only 6, there's only 5, there's only 4, there's only 3, there's only 2, there's only 1. And if we want to know all the different permutations of those books, if we want to know total how many there are, what do? We multiply all those. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 would give us our answer. But remember, there is another way that we can represent this. We don't want to have to write 10 times 9 times 8 times 7 times 6. So the other way we could write this is 10 factorial. That's what we talked about last time. It's exactly the same thing. And if you do that, put 10 factorial in your calculator or go 10 times 9 times 8 times 7 times 6, you will get the answer 3,628,800. Okay, it's a very big number. So it turns out for these type of questions where you're organizing n objects and you're organizing all of them, you're not leaving some out, what the equation will always be is n factorial, right? In this case we were looking at 10 different books and we're arranging them all and we end up doing 10 factorial. So the next question, it's pretty fast. If you see it's this type, determine the number of permutations of 5 candidates' names on a ballot. So you're going to put 5 people's names on the ballots and everyone's arguing over whose name should go first and second and third, and you want to go think to yourself, well, how many different permutations are there? How many different ways could we write those names? Well, again, you could either do it the slow way, use the fundamental counting principle, and say to yourself, how many names could you put in the first spot? You could put 5 names because there's 5 candidates. How many in the second spot? There's only 4 left. There's only 3. There's only 2. There's only 1. Multiply those all together and get your answer. Or the other way you could do it is you know that this 5 times 4 times 3 times 2 times 1 means 5 factorial. And that's what the formula told us up here. If you're trying to get the number of permutations of n distinct objects taken all at a time, it's n factorial. In this case, n is 5. So 5 factorial equals 120. A baseball coach is determining the batting order for the 9 players he is fielding. The coach has already decided that he wants the pitcher to hit last. How many different batting orders are possible? Okay, again, for all these questions, you can use the fundamental counting principle if you want. It's just a little bit faster if you learn how to do it without having to put all these spots down and everything. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You already know that the pitcher is going here. I'll put a P for pitcher. So how many more people do you have to place? You have 8 more people to place. How many possible names could go in the first spot? 8. Can't have the pitcher's name. He goes here. So 8 times 7 times 7. Hey, why don't we just stop this charade and do 8 factorial? Right? Which is 8 times 7 times 6 times 5, blah, blah, blah. And if you do 8 factorial, you'll get 40,320. So, you know, we already did questions of this type. We just didn't call them, we didn't know they were permutations specifically, and we didn't really have the formula, but there you go. But it's just like the stuff we already did. Now, here's some stuff that's new. This time we're going to look at, actually this isn't new either if I really think about it. We did questions like this too. This type 3, which we'll do next day, is new, but we actually did questions like this as well. So type 2 is number of permutations of n distinct objects taken r at a time. So this time you might not be taking all of them. Like, you know, for example, the 10 different books. We arranged all 10 different books on the shelf. But what if we had those 10 different books and we didn't arrange all 10 books? We only arranged 4. You're just going to put 4 of those books. So we're going to answer that question in just a couple minutes. What the heck? Let's go to that. I'm kind of jumping all around here, but let's go to that question right now. So we have 10 books, just like before. Same books if you want. And you're going to only put 4 of them on the shelf. So let's say there's not as much room on our shelf. We can only put 4 books on the shelf. So here's our spots, 1, 2, 3, 4. How many books could you choose from in the first spot? You could put any of the books, so you could put 10 books in the first spot. Now you've used 1 book, so how many could go in the second spot? Just 9. How many could go in the third spot? Well, you've used 2 already, so there's only 8 left. And then in this time, there's only 7 left. So there you go. If you multiply 10 times 9 times 8 times 7, you'll get your answer. Can you think of another way you could write that using factorial notation? It kind of looks like 10 factorial on top, but it's not, like it doesn't go all the way down to 1. It stops at 7. So what would be, you could put a denominator here and it would cause this. Can you think of what the denominator would be? It would be 6 factorial, right? If you think of it, 10 factorial is the same as 10 times 9 times 8 times 7 times 6 factorial, and if you have 6 factorial on the bottom, they cancel and you're left with exactly what you want. So that is how it would look in factorial notation. Now, how did you get this 6? Like, where did this 6 come from? How could I just look at the question here and get the 6? Well, if you look, we have a 10 here and we have a 4 there. What would you do with those numbers? You'd subtract them. And so that is how you're going to get the formula in this case. So I'll come back to that question. I'm really jumping all over the place. But if you want to get the permutations in this way, the formula is n factorial, just like it was before up top. But this time, since you're not going all the way down, you're not using all the numbers, all the objects, you do n minus r factorial on the bottom. So again, if I jump ahead, n factorial over n minus r factorial. N is the total number of objects, in this case 10. This is our n. R is how many you're actually arranging. We're arranging 4. So it would be 10 factorial, because n is 10, over 10 minus 4 on the bottom, factorial. And 10 minus 4 is 6. So do you see we get exactly what we wanted to have right there. By the way, 10 times 9 times 8 times 7 equals 5,040. So we're now done that question, but let's go back. I also wanted to show you the way you represent this permutation of n distinct objects taken r at a time. There's 2 ways you can, actually there's more than 2, but the main 2 ways you'll see it is either like this, npr, like that. This is the permutations of n objects taken r at a time. Or the other way you often see it written is like this, permutation n comma r. And either way, this is your formula. So this is something you want to remember. Okay, now, still jumping all over the place, let's go back up here and I want to show you why the formula here is just n factorial. Okay, let's actually look at this question right here. So in this case, we're taking 10 different books. That's our n value. And we're going to arrange all of them on the shelf. So how much is our R value if we're arranging all of them on the shelf? The R value is also 10. So again, look at your formula down here, n factorial over n minus r factorial. So we have n factorial over n minus r factorial. Okay, n is 10, so we have 10 factorial over 10 minus r is also 10 over 10 minus 10 factorial. So we get 10 factorial over 0 factorial. Hope you remember from last time, what's 0 factorial equal to? 0 factorial equals 1. So you get 10 factorial over 1 or just 10 factorial. This is actually one way you can kind of prove that 0 factorial has to be equal to 1, because we already knew that the answer in this case was 10 factorial. The only way you can equal 10 factorial here is if 0 factorial is equal to 1. So it's another way you can show that 0 factorial is equal to 1. Similarly up here, if I'm taking n distinct objects and I'm taking all of them at a time, that means that really what I'm doing is the permutation of n number of objects and taking n at a time, taking all of them at a time. And again, if I use my formula that's from below, it would be n factorial over n minus n factorial. That's n factorial over 0 factorial. That's n factorial over 1. So you're just left with n factorial, and that's what we already said the answer was there. Okay, so this equation, this formula right here, actually works even for the first case, where you're taking all the objects at once. Notice that r has to be equal to n, that's like up here, because you're using all the objects, or r has to be less than n. But it doesn't make sense to have r bigger than n. That'd be like having 5 objects and arranging 10 of them on the shelf. Well, there's only 5 of them. That doesn't make sense. Alright, boy, we were jumping around here. So next thing, we're jumping here. I'm going to jump to websites now. We're going to use a calculator to determine the permutation of 12, choose 8. So there's 12 objects, 12 distinct objects, and you're going to arrange 8 of them. Order matters here, so you're going to arrange 8 of them. So it's not a difficult question, since you're allowed to use a calculator, as long as you know how to use your calculator. So you're going to have to take your calculator and figure it out. I found online a couple calculators, and there's 2 main ways that you do these. One way is, see, here's your NPR right there. So one way is you hit the NPR button, and then you put the 2 numbers in, first the N and then the R with a comma in between. Okay, so I've hit the NPR button. Now I'm going to hit 12, then I hit comma, and then I put 8. You can close the bracket if you want. You probably don't need to. And you hit equals, and here's your answer. Gosh, how much is that? 19,958,400. Okay, so that's one type. I actually think this is less common to have it this way. The way that's more common, I think, is this type of calculator, where first of all you put the first number. Remember, it was permutation of 12 distinct objects where you're arranging 8 of them. So first you would put the 12, then you would hit the permutations button, which is right here. Now, unfortunately, in this online calculator, they don't show it, but usually what you do is when you hit this button, a P would show up after the 12. In this case, nothing happens, but I hit it. It really did work. And then you hit the 8, and then you hit equal, and you get the same answer as well. That's the way I bet most of your calculators work. The only difference is when you hit 12 and then the NPR and then 8, it'll show on your screen 12P8. Okay, so figure out which one works for you or which one works for your calculator, and then you can use it through all these questions. So I'll just write the answer down here again. It was 19,958,400. This question we already did. Is there anything else to say about it? I don't think so. Okay, a popular rock group has written 30 songs from which it selects to perform at a concert. How many different opening sequences of 3 songs can be performed? Okay, so the crowd's out in the audience, you know, they're ready for the concert to begin, and the band's backstage, and they're saying, you know, we want to really come out strong here. We want to come up with the best group of opening 3 songs we can. So let's go through all the options, and we'll discuss this. Okay, so how many different combinations are there? Well, what we have here is 30 songs, so that's your N. But you're not arranging all of them. We're only interested in the first 3 songs. So you're only arranging 3 of them. That's your R. So what you're trying to do is 30 distinct objects. This is permutation because order mattered, and you're putting 3 of them. You're ordering 3 of them. So if you wanted to, you could do this by the fundamental counting principle, right? You could think to yourself, I have 3 songs to start with. to start the concert with. How many songs can I choose for the first spot? 30. How many can I choose for the second song? 29. How many for the third? 28. And I could go 30 times 29 times 28 and get my answer. In some ways, I think it's easier to do it that way. Then you're not worrying with which formula to use and all that kind of stuff. I mean, it just makes logical sense that that's what you would do here. But if you understand the formulas, then you would do this right there. And you know that the formula is n factorial over n minus r factorial. So that would be 30 factorial over 30 minus 3 factorial. Do you see how much longer this takes? So that's 30 factorial over 30 minus 3 is 27 factorial. 30 factorial can be written as 30 times 29 times 28 times 27 factorial over 27 factorial. The 27 factorials cancel, and you're left with 30 times 29 times 28, which is exactly what we have here as well. Okay, if you multiply that out, you get 24,360 songs. So the audience better be patient, because they've got a lot of discussion to do to figure out the best option. All right, Tanya needs to create a password. It can use any digits from 0 to 9 and or any letters of the alphabet. So you can use all digits, you can use all letters, or you can use letters and digits. The password is case sensitive, so you can use upper and lowercase letters. A password must be at least 5 and a maximum of 7 characters long. Each character can be used only once. Now that's not too realistic, so our answer is actually going to be smaller than if you could repeat characters. How many different passwords are possible? Most passwords you can repeat characters, but in this one you can't. Okay, the first thing you better figure out is how many characters are there? Well, you have the digits 0 to 9, so how many of those are there? 10. Plus you have all the letters, there's 26 of those. But here's the thing, it's case sensitive, so you can either use those upper or lowercase. So you don't only have 26 here, you have 2 times 26. So that's 10 plus 52, or 62 characters. Okay, there's 3 different situations here. It depends on how long your password is. If your password is 5 characters, you're going to have to do one thing. If your password is 6 characters, you're going to have to do another thing. And if your password is 7 characters, you'll have to do a third thing. So I'm not going to show as much of the math this time. I'm just going to use that formula. So here's my permutation. What numbers goes in the front here? How many objects are you arranging? You have 62 distinct objects, so it's going to be 62 and 62 and 62. The only difference is in this first one, when you have 5 characters, you're going to order 5 of those 62 distinct characters. In this part, you're going to order 6 of those distinct 62 characters, and this one 7. Okay, so you can do this or that. So what does that suggest you're probably going to do with all 3 of these answers? Since it's or, you're going to be adding. So you're going to get this answer, this answer, this answer, add them together and get your final answer. I'm making a big box here. You know why? Because this is a big answer. So 62 P5, the permutation of 62 distinct objects where you're ordering 5 of them. You can take your calculator if you want, or you can just trust me. It equals 776520240. Wow. So what do we got there? 776,520,240. Now that's if you're ordering 5. If you're ordering 6 of them, you end up with 4,4,2,6,1,6,5,3,6,8,0. So what do we got there? 44,261,653,680. And if you're doing 62 of them distinct objects and you're arranging 7 of them in order matters, you get this colossal number. And remember, in a real password it'd be more because you'd be able to repeat. We're saying you can't repeat any of the characters. I hope I know how big this number is. What's this? This is thousands, millions, 2 trillion, almost 2.5 trillion. You add those all together, you get 2,523,690,780,000 different permutations. I feel pretty safe about my password. Mind you, with powerful computers, they could zip through those in a pretty short amount of time. Okay, that's it for today. What we're going to do next day is we're going to look at the third type of permutation problem. This was where you have n objects, just like before, you have n objects, but some of them are alike. So A objects are alike, another B objects are alike, another C objects are alike. So in this case, you have repeated objects. So just to give you a very quick example of that, we're not going to solve it, but just to give you an example of that, you know how so far we've answered lots of questions. I think I used this word before, pickle, and I asked you how many ways are there to arrange the letters in pickle to get new 6-letter words if you had to use all the letters and you couldn't repeat them. And you said to yourself, well, there's 6 letters, so it'd be 6 factorial. But what if it wasn't pickle? What if the word was onion? Do you see why this is going to be different? Well, one reason it's going to be different is there's only 5 letters, but the answer is not going to just be 5 factorial. Why not? Because you have 2 N's and you have 2 O's. So you need to recognize when you're rearranging these letters that putting this N first and this N last, right? Let's say I have this N first and then I have that O-I-O-N. That's one arrangement, isn't it? But now let's put this N first and this N last and keep the other ones the same. Wait a minute, those look exactly the same. So we have to take that into account, that we have these repeated objects that we have to not count twice or multiple times. Okay, a little bit more confusing. We'll do it next time.